Hello, welcome. So, in this is a three-part series of an episode, three-part series of lessons, and we're going to be talking about Cayley's theorem. So, however, before we begin, first of all, I'm going to do two videos where I motivate Cayley's theorem, but in this particular video, we're going to talk about what are the prerequisites, right? We're going to come up with some prerequisite knowledge for understanding Cayley's theorem. Alright. Prerequisite knowledge for Cayley. Alright. So the idea is, in order to understand Cayley's theorem and what it's really saying, it's important to understand what a homomorphism is, a homomorphism, and also understand what an isomorphism is. Alright, so really at the very base, a homomorphism is a function. Right? It's a function between two groups. But one really cool thing about it is it tends to preserve group structure. So that sounds kind of abstract, but what we're saying is, look, phi, let's think of phi as a function, right? Phi is a homomorphism from a group G to another group H. Right? That means it's some sort of function, and it does certain things. For instance, it takes in, obviously since it's a group, the group has its own multiplication or its own operation. It takes in two elements, G1, G2, right? And then splits out phi, what G1 would give you if you applied phi to it, multiplied by what G2 would give if you applied phi to it. And this multiplication now becomes multiplication in the group H. So if we say that multiplication in the group G is a dot, then multiplication in the group H would be like a cross. So really what we'd be saying is a homomorphism would be it's a function from one group to another, and it has the property that it takes, first it has to be a function, of course, and the first property is that it takes in G1, G2, and then sends it to phi of G1 times phi of G2. But this feels very abstract, so let's get a little more specific. Let's work with actual groups here to know what we're talking about, right? So let G be, we're going to set G to be the group R, that is the set of real numbers, and we are going to set H to also be, sure, we could set H to also be the group of real numbers. Why not? Right? In this case, it would be like real numbers greater than or equal to 0. So let's write it that way. Set of all real numbers greater than or equal to 0. Okay. So we're going to define a function phi from R, which we're calling G, to, let's say, R greater than or equal to 0. Actually, let's say R plus. That is the set of all positive real numbers. Alright, I made an error there. Let me erase that. Right, so what we're going to do here is we're going to define the function as follows. Phi is going to take any real number that we get here. It's going to take any real number x, and what it's going to give us is e raised to the power of x. Right, e is just the exponential. So let's check if this is a homomorphism. For it to be a homomorphism, first it has to be a function. Is this a function? Well, how do you check that something is a function? The most important thing to check is that it's not one to many. Right? And is it true that for different values of, if you have two real numbers x and y, right? If we have a real number x, can e to the x take on different values? Well, the answer is no, right? Because we also know what the graph of e to the x is. Right? It looks kind of something like this. So at 0, let's call this x, and let's call this y, let's say, right? Or in this case, we just say phi of x. Why not? Might as well use what we're being told. So phi of x right there. So what happens is at x equals to 0, what's e to the 0? That's just 1. So we have this point, and the graph of e tends to go like that, right? It's an exponential, right? So it goes, woo, that's e of x. And what you notice is that in this particular point, this function fails satisfies the vertical line test. That is, every x value corresponds to one and only one phi of x value, right? And that tells us that the function is not one to many, right? It doesn't associate one thing with many things. So, which means that phi is actually a function. So we're good. But we're not completely good, because to show that something is a homomorphism, it has to be a function, but it also has to satisfy this weird property that if you get two values from the group G1 times G2, the answer is equal to phi of G1, which I've used equal to phi of G1 star phi of G2. But that's kind of abstract, so we're looking at an example. Here we're considering the group R. Here the set of real numbers is being considered under addition. So let's put that there. This is the real numbers being considered under addition here, and the real numbers here being considered under multiplication. Alright, so I hope that's not confusing, right? So basically, what the idea would be saying is that we need to check that phi applied to G1, G2. What's G1, G2 in this case is two real numbers. So let x and y be two real numbers. X, y. And over here, remember what we're saying is we take two elements of the group and multiply them with each other. And this dot was the operation for whatever the group is. So in this particular case, what's the operation of our group here? Well, in this case, the operation is addition. So we're saying that phi of x plus y must then be equal to phi of x, right, star phi of y, right? Sorry, that's phi of y. All right. Let me erase that again. Another mistake. So, right. So that's what we have right here. No pen, pencil. All right. So that's the situation we have now, right? So we're saying that phi of x. What's times here? Times in our case is the star here. The star would be the operation for this other group here, and this group is being considered under multiplication. So really, we're trying to see is phi of x plus y equals to e of x times, right? Because the operation is multiplication here, times e of y, right? Because remember, phi of x equals to e to the x. So phi of x will be e to the x. Phi of y will be e to the y. So the question we're trying to ask ourselves is phi of x plus y equals to e to the x times e to the y? Right? That's a question. We don't know that yet, right? That's a question. And if we can show this, we have ourselves a homomorphism, because it's a function and it satisfies the property that phi of x plus y takes phi to the x times phi to the y. Okay, well, is this equality true? Let's check it out. What's phi of x plus y? Phi of x plus y, from the idea, remember phi of x was being set to e to the x. Phi of whatever you plug in here gives us e to that thing. So phi of x plus y will then give us e to the x plus y. Okay? But e to the x plus y from algebra, we know that's the same as e to the x times e to the y. So it turns out that phi of x, and what's e to the x? Well, e to the x is phi of x, right? Phi to the x gives you e to the x times, what's e of x? E of y, e to the y, that's phi to the phi of y. Right? So indeed, phi of x plus y equals phi of x times phi of y. So we have ourselves a legitimate homomorphism here between the set of real numbers and the set of positive real numbers. Right? We have ourselves a homomorphism between the. It's not actually, I said it's a group, right? The group of positive real numbers. Okay. So that's one example of a homomorphism, right? Maybe we want to try another homomorphism. Sure, why not? Let's try this homomorphism. So what we're going to do is we're going to consider. Let's say that G is our group, and let's say that G equals to 2 to the 0, 2 to the 1, 2 squared, 2 cubed, right? And then let's stop right there. So let's say this is our group, and over here we're assuming that 2 to the 4 is just going to give us 0 again. Alright, so we're assuming that 2 to the 4 equals to 1. Alright, that would mean that 2 to the 5 would just be okay, I don't know if we actually need to work out all the multiplications here, but alright, so the idea is, if we were to write this group even better, I would say this is the set, G is the set of all 2 to the x, such that x is an integer and x is, right, that's what it is, between 0 and 3. So obviously if you run over, we just work mod this in this case we'll be working mod 3, right? So For instance, 2 to the 4 will be equal to 2 to the 4 mod 3, which is just 1, which just gives you, no, sorry, we're saying 2 to the 4 is the same as 2 to the 0. That's just 1. Okay. So we're really working mod 4. Sorry. Yeah, so 2 to the 4 will equal to 2 to the, what's 2 to the 4 mod 4, right? What's 4 mod 4? That's just 0. So that gives us 2 to the 0, which is 1, right? And that's the same with other values. So for example, what's 2 to the 2 times 2 to the 3? First that will be 2 to the 2 plus 3, which is 5. And mod 4, that will be 2 to the 5 mod 4 here, right? Because 5 is not one of these powers. We want to figure out what power it's equivalent to. And 2 to the 5 mod 4 would just give us 2 to the 1. So really what we're saying here is that 2 to the 5 is the same as 2 to the 1. Right? So if you actually do the if you check, you'll find that this G satisfies all the axioms of a group. So we're going to call that our first group G. And then what we're going to do is we're going to call our other group H. So H is 2 to the x, such that x is between 0 and 3. And then our other group H is going to be the group, let's say the group of, what, just, let's call it the set of all integers. Yeah, let's call it the set of all integers under the operation of addition. Alright? So here we're saying these elements under the operation of multiplication. So let's see if we can construct a homomorphism phi from the group G, right? Our group G was the set of all powers of 2 to the x, right? Remember, it's this thing here. This is G, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And we're considering G under multiplication because we're multiplying 2 to squared times 2 cubed, for instance. And we want to construct a homomorphism phi from G to, we're going to send it to Z plus. That is the set of integers under addition. Okay? So how do we define this homomorphism? Well, we're going to say this. Phi is going to take in a group, is going to take in an element of G, right? It's going to take in some G1, some element of the group. So what do the elements of the group look like? Elements of the group look like 2 to the x, where x is of course between 0 and 3, and the x is an integer. And we're going to let it take phi of 2 to the x and just give us x back, give us the power back. Right? This is x. No confusion. This is x, right? Handwriting is a little messy here. So this is going to be, we're claiming that this is a homomorphism. Well, how do we check that something's a homomorphism? First, it just has to be a function. Is this a function? Can 2 to the x ever give you any other value other than x? Well, I mean, we can check here that that's just not going to happen, because x is its own real number and its own integer, and so x can't be simultaneously, can't be two different things. For example, if x was 2, there's no way x is going to become 3 over here, right? So it makes sense that whatever value we plug in here, 2 to any power, and if we're pulling out the power, well, the answer we get is always the same. The power is always going to be the same here. It's not going to, the power is not suddenly going to break up into two different things. So for instance, 2 cubed, phi of 2 cubed, right, will just give us 3. There's no way it's going to give us like 4, because 3 is 3. It's not going to become 4. And that's the idea here, is that, so one value, phi of 2 to the 3 only gives you 3. In the same way, phi of 2 to the x only gives you x. But that's not enough to show that something's a homomorphism. The second thing we need to show is that if you get any two values of G and you apply the group operation under them, G1 times G2, well, the end result is going to be phi applied to G1 times phi applied to G2. So let's check that that is true. Okay, so how do we do that? Well, we need to take two values from this group here, G. So let 2 of x, 2 to the x and 2 to the y be elements of G, right? We're allowed to do that. If that is true, then we need to check that phi of 2 to the x, right, under we're looking at things under the operation. For a group G, the operation is just multiplication. So we need to check that phi of 2 to the x times 2 to the y is actually equal to phi of 2 to the x times phi of 2 to the y, right? That's what we need to show. Right, so In this case, we can actually just start, but we don't know if this is true. If this is true, then we have ourselves a legitimate homomorphism, right? So let's see if that is true. So, well, it turns out that phi of 2 to the x, well, okay, so how do we show that this equals to phi of 2 to the x times phi of 2 to the y? Well, one thing we notice is that phi of 2 to the x, by our definition of phi, is just going to give us x. So phi of 2 to the x is x, and phi of 2 to the y is just y, right? So really showing that phi of 2 to the x times phi of 2 to the y equals to this amounts to showing that phi of 2 to the x times 2 to the y really equals to this, right? And remember our times operation, right? Remember that our times operation here is, for our group Z, our times operation is a plus actually, right? So the operation is addition. So really what this amounts to showing is that we really need to show that phi of 2 to the x times phi of 2 to the y actually equals to phi of 2 to the x plus phi of 2 to the y, but which phi of 2 to the x is just x, and phi of 2 to the y is just y. So we're saying that what we really need to prove is that phi of 2 to the x times phi of 2 to the y is really equal to x plus y, right? Is that true? Well, let's examine that. Phi of 2 to the x times 2 to the y, 2 to the x times 2 to the y from just algebra is 2 to the x plus y. And so we're saying that is that equal to x plus y? Well, yeah, let's check that. Well, our formula says phi of 2 to anything just gives us that thing back. So here we have phi of 2 to the x plus y. That means that phi of 2 to the x plus y is just x plus y, right? It's going to take the power and give us that back. But that turns out to be exactly the same as what we said here. So indeed, and right, because phi of 2 to the x plus y equals x plus y. And we know that phi of x, as we saw before, phi of 2 to the x, right, we just saw that here. And so this x can be replaced by phi of 2 to the x, and this y can be replaced by phi of 2 to the y, right? So indeed, we have ourselves a homomorphism here, right? So this is actually a homomorphism between the group of just powers of 2 less than or equal to 3, and the set of all real numbers here, z plus. All right. So that's what a homomorphism is. And it's really a function, and it's a function that takes you from one group to another, right? So let's write down, a homomorphism is really just a function from one group to another. So first you have to check that it's a function. These are groups, and if this group has the operation dot and this group has the operation star, then phi, to be a homomorphism, has to have this following property, that g1 times phi of g1 times g2 actually equals to phi of g1 times phi of g2. Actually, in this case, it's going to be the operation of the other group. That's what we call a homomorphism, right? So why is a homomorphism important? One thing is that it's said to preserve what is called group structure. So for instance, the cool thing about it is, if you get, like, let's say, I mean, I'm not going to prove this, but you can work them out. So if you have a homomorphism from a group to a group, and you take the identity from that group, phi applied to the identity of the group G is going to give you the identity of the group H. Right? That's remarkable. Another thing you notice from here is that, and again, this can be proved. I leave this as an exercise to you to prove that. Another thing that we note is that phi takes every element. So if you get an element of the group, right? If you get an element of the group, like let's say G1, right? If you want to figure out, well, let's say you want to figure out, you know what G1 inverse is, but you're wondering what's the inverse of phi of G1. Right, so how do I explain this better? So the idea is, okay, let's say G1 is an element of G, okay? Well, since G is a group, it has an inverse. Call it G1 inverse. Right? A natural question you may be wondering is, well, what's the inverse of phi of G1? That is, if I get G1 from G and send it to H, right? That's what phi does. Well, what's going to be the inverse of where G1 is sent? That is, phi of G1 is now in H. So what's the inverse of this thing in H? Well, it turns out that the inverse of phi of G1 in H, that is, it turns out that phi of G inverse is really the same as phi of G1 inverse. That is, if you get the inverse of G1 in G, and then you apply phi to it, what you get is actually the inverse of phi of G1. Right? So that's really another remarkable fact. And it sends elements to themselves, inverses to themselves. So it sends identity to the identity, inverse to the inverse. And why is this important? It means that the image, right? So if you send phi, a function phi, from a group to some other group, well, this function, let's say it's a homomorphism. This homomorphism does not necessarily have to be surjective. It doesn't hit everything. Let's see why that is true. So for instance, a surjective, or what's called an onto map. So in this particular case, for instance, we had the group which was the powers of 2, right? We had 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And over here we had just the integers under addition. Now what turned out happening is that, sure, we sent every 2 to the x to x, right? But remember that x was only between, really, we're only considering x between 0 and 3 here, 0 and 3. But you see, how many integers are there? Definitely more than 3. There are infinitely many. So if you were to think about what's the image of this function, what's the image of the function phi? Well, if it only takes in powers 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3, and gives us 0, gives us 1, gives us 2, and gives us 3, then this map is not surjective. That is, it leaves out many integers, so it's not an onto map, because the set of integers is infinite, and this function is only hitting 0, 1, 2, 3, right? So it's not a surjective map. Sometimes it is, but it's not always a surjective map. And we had the same thing here as well. So we had our other homomorphism here, where we took, well, it was a homomorphism from the set of positive real numbers. Well, maybe this one actually works. All right. But the idea is that the homomorphism doesn't have to be surjective. Okay. Why do we care about this? Although the homomorphism doesn't have to be surjective, it turns out that the image of a group, the image, right? This is now referring to the image. That is, if you get every element of the group, and if you get G1, if let's say the group has elements, it doesn't have to be finite, but let's say we have a finite group, right? G1, G2, all the way to Gn. So we have ourselves a finite group there. And then we consider, well, phi of G1, right? That will give us something in H, right? That's what the function does. Then we consider phi of G2, all right? And all the way to phi of Gn, all right? So this gives us some other subset of H, all right? So we're actually going to call this phi of G. That is the image of the entire group, is phi, where phi sends everything in the group. G1 is sent to phi of G1, G2 is sent to phi of G2, G3 is sent to phi of G3, Gn is sent to phi of Gn. Right? And phi of G is that, otherwise known as the image of phi, right? And so the natural question to think about is, okay, fine. As we said, this map phi doesn't have to be surjective. It doesn't have to be onto. What that means is that there may be elements of H that are left out, right? So what that means is that we know that phi of G, right? All these elements are in H. So we know that phi of G is a subset, right? We know that phi of G is a subset of H, right? That we know for sure, right? Because all these elements are in H, so it's a subset of H. But because it could be a proper subset, that is, since the phi is not surjective, this could end up being a proper subset, where there are certain elements in H that are not in here. So a natural question to think about is, well, does this thing still remain a group? Okay, it's a subset of H, but is it a group? Is the image of phi still a group? It turns out that it actually is. And the reason it is because of these properties we've been talking about here, is that it takes the identity to the identity and the inverse to the inverse. Alright, so I don't know if we want to prove that or not. Sure, why not? Why not? Let's have some fun. Okay, let's prove that if phi is an isomorphism from a group G to a group H, is a homomorphism, sorry, from a group G to a group H. We want to prove that the image of G, otherwise known as phi of G, right? Phi of the big G, which is, as we said before, is just, well, you get every element of the group, apply phi to it, phi to G1, phi to G2, phi to all the elements. It could be infinite. I just used finite to show what I was talking about. This set here of where everything is sent is what is called phi of G, or the image of G. And we're wondering if is the image of G also a group, right? And if, of course, if phi of G, the image of G, is a group, then it must also be a subgroup of H, right? That's another thing, this subgroup. Well, how do we show that how do we check if phi of G is actually if it's actually a group? We just check if it satisfies the properties of a group. Well, does it have the identity element? Yes, because we said that it's for homomorphism. If you get the identity of G and you apply phi of E to the G, what you end up getting, so if you get the identity of E in G, so the identity of G, which is E sub G, if you apply phi to it, you end up getting the identity in H, which means that the identity in H is also an element of phi of big G, right? It's in the image of phi, which means then that E sub H is, the identity is in phi of G, right? So that's a good sign if we're trying to show that something is a group. So phi of G has the identity. The other thing we're trying to prove that phi of G is a group. The other thing we note is that, well, does phi of G have inverses? Okay, so what we said before is, well, let's say that G1, let's say that, right, I mean, every element of phi of G is of the form phi of G1, right? For some G1, in G, right? That's what it means to be in the image, of phi, right? So that means that every element of phi of G is of the form phi of G1 for some G1 in G. So a natural question to think about is, well, if phi of G1 is an element, we've said phi of G1 is an element of the image of phi, is in phi of G. Well, a natural question to think about is, well, if phi of G is really a group, this thing here must have an inverse. Does it have an inverse? It turns out that it does, and that was the other property we said. We said that if you're in a homomorphism, then every element, if you want to figure out what phi of G1 inverse is, if you want to look for phi of G1 inverse, that turns out to just be phi of the inverse of G1 in G, right? G1 inverse, right? That's where the properties as mentioned before are really important, because now this also turns out to be true. So phi of G1 has an inverse, okay? And then the other thing we need to check is associativity. But associativity follows because H is a group, phi of G is a subset of H, and since we're using the same operation as in H, it means that because associativity holds in H, associativity also holds in phi of G, right? That's kind of clear, right? Phi of G just inherits associativity from H, right? That is, maybe to be more clear, like let's say we have elements phi of G1, let's say phi of G1, phi of G2, phi of G3 are elements of our group, right? Let's say that's true. Sorry, the elements of, not our group, but the elements of phi of G, the image, right? This is phi of G, it's supposed to be. Okay, that's written badly, maybe too badly. Let me erase. Alright, so okay, let's say that phi of G1, phi of G2, phi of G3 are elements of phi of G. To show associativity, we need to show that phi of G1, right, times phi of G2 times phi of G3 is really the same as phi of G1 times phi of G2 times phi of G3. Right? That's what we need to prove here, that these things are actually equivalent to each other. Alright, so that means the order multiplication doesn't matter. All these are elements of phi of G, the image. Well, this is actually true because phi of G1 is still an element of H, right? Remember, phi was a function from G to H. So phi of G1 is in H, phi of G2 is in H, phi of G3 is in H. This operation of multiplication is also in H. So because this product is the same as this product in H, this product is also the same in phi of G, in the image of phi. That's what we're saying here. So associativity holds. The only property left to prove is closure. What does that mean? Well, it means that if we get two elements in the image of phi, that is, if we get two elements of phi of G, is it true that when you multiply them with each other, you still get an element of phi of G? That is phi of G1 times phi of G2 always an element, right? Is this product always an element of phi of G, that is the image of phi, right? It turns out, let's see if that is true. Well, phi of G1 times phi of G2, right? How would we show that something is an element, is in the image of phi of G? Well, all elements of phi of G are of the form phi of x, right? Of the form phi of x, where x is an element of G. But that's what it means to be in phi of G. So all we need to show is that this element can actually be written in the form phi of x for some x in G. Well, can you see how this follows? Well, phi is a homomorphism. So remember, one of the defining properties of a homomorphism is that phi of G1 times G2 equals phi of G1 times phi of G2. Right? So if we know that phi of G1 times phi of G2 is then equal to phi of G1 times phi of G2, because phi is a homomorphism, right? So I've just phi of G1 times phi of G2 is actually equal to phi of G1 times G2, right? That's what it means to be a homomorphism, right? But then if phi of G1 times phi of G2 is of the form phi of G1 G2, then it means that this is clearly an element of phi of G, because it takes G1 and G2. G1 is an element of G, G2 is an element of G. Since G is a group, G1 times G2 is also in G, right? Because the group is closed. So that means that this element here, phi of G1 G2, is actually an element of phi of G. That is, it's in the image of phi. And it also turns out, which also means that because this is equal to that, it means that this product here of two elements in the image of G gives us an element in the image of G. So the image of G is closed. We just shown that. We showed that associativity holds for the image of G. We showed that the image of G has an identity, namely the identity of H. That is, if you get E of G, the identity in G, and apply phi to it, you get the identity in H. And we've shown that it has an inverse, right? The inverse of phi of G1 is actually just this. We found an inverse for every element. If this is true, well, then that means that the image of G, phi of G, is really a group, right? So that's one interesting thing about a homomorphism, because that's really what we're saying here, is that, look, why do we care about homomorphisms? Well, if phi is a homomorphism from a group to another group H, all right, then it means that, it follows that the image of G, right, if it's a homomorphism, of course, we know what the properties are. It follows that the image of G, which is just where we get every element of G and see where they're sent, the image of G turns out to be a group. And in fact, it's a subgroup of H. Right. So basically, phi, you could think of phi, a homomorphism, as a sort of function that takes us from one group to another, but has the interesting property that the image, it always preserves, it always gives you a group at the end of the day. That is, it sends you from another group to another group, right? Right. And even if it's not surjective, even if it doesn't hit all of H, whatever phi of G is, whatever subset of H phi of G is, that subset is also a group. That is, it's a subgroup of H. So that's an important property. So the way mathematicians like to say this is that a homomorphism preserves the group structure, in the sense that it takes a group and still gives you another group. The image of the group is another group. Right? That's one important thing about having a homomorphism. So I guess just a recap of this is a homomorphism is a function from a group to some other group. We said that its image is a group. Right? That's important takeaway here. The image is a group. In fact, since phi of G is in H, that means that phi of G is a subset of H, but it's also a group. And since H is a group, we also see that phi of G is a subgroup of H. Another thing we know for homomorphism is that for something to really be a homomorphism, it means that it must take any two elements of the group and be equal to phi of G1 times phi of G2. Right, that's another property. This is the defining condition of a homomorphism, right here, this one here. Defining condition. It takes in two elements and then G1 and G2 and gives you G1 times G2. Right, phi of G1 times phi of G2. That's what I meant. Right, so that's really, and remember homomorphism is a function, right? So you have to check that it's a function first before you even check if it's a homomorphism. Alright, then, so that's what a homomorphism is. So now the question is, well, what's an isomorphism, right? Sounds kind of similar. We still have the morphism, homomorphism, isomorphism. So what is an isomorphism? Well, is it related to a homomorphism? Yes, your intuition is right. Well, an isomorphism is a homomorphism that is a bijection. What does that mean? Well, we said that phi from G to H, right? Well, if let's say that phi from G to H is a homomorphism, right? And we know what that means. We said already what that means. We said that if phi is a homomorphism, that means that it takes an element of the group. It's a function, and it takes two elements of the group, and phi of G1 times G2, that is, when you multiply them in the group, the answer is the same as if you'd sent G1 to H first by getting phi of G1, and G2 to H by getting phi of G2, and then multiplied them later using the group operation for H. Maybe I should write it like this. Here I'm saying that the operation for H is this, the multiplication operation for G is that. So that's what it means to be a homomorphism. But I mean, the key thing is that a homomorphism is a function. So but we said before that if phi from G to H is a homomorphism, it doesn't necessarily mean that it's a surjective map, that it's not onto. It's possible that the elements in H, that is, it's possible that phi of G, the image of phi of G, that is, there are certain elements of H that phi of G never hits. That is, phi of G may be a subset of H, but it is not necessarily equal to H, right? That's possible, right? So, but one wonders, well, what if phi is a function? So here we're saying if phi of G does not equal to phi of H, so if phi of G does not equal to H, then it means that phi of G is a proper subset of H, right? So a natural question to ask is, well, in that case, it will not be a bijection, right? A bijection just means you're not one-to-one and you're not onto. So that means that phi is not a bijection. So a natural question to think about is, what if phi is a bijection, right? What if phi is a bijection? What happens then? What if phi is a bijection? That is, phi is a homomorphism, but it's also a bijection, which means that phi of G equals to H, right? And phi as a function, right? This means that the image of the function is H, that is, the map is surjective or onto. And the other thing is, to be a bijection, you have to be one-to-one, right? So, or otherwise known as injective. If phi of G to H, if phi is a bijection, then it means that phi of G equals to H, and phi is injective as well. That is, phi is both injective and onto, right? Injective and surjective. Hence, it is bijective. What happens then? Well, if phi is a bijection, that is, if phi is a bijective, now we're going to use the word. If phi is a bijective homomorphism, right? Then we say that phi is now an isomorphism. Right. So an isomorphism is simply a homomorphism that is bijective, where the function is actually a bijection. And why is this important? If a homomorphism is bijective, then it means that this group and this group are in a sense the same. So that's what it means. That is, if phi, so if you have one group and you have another group, and you're wondering, well, are they really the same? Okay, they may look different, right? So for example, there are probably a couple of groups that you've looked at that looked very similar to you. So for example, we have, I don't know if I want to go there, but sure, well, maybe we can do it. Why not? So, like, there's this group here. One, you start from the identity. You start from, let's say, the one we looked at. Let's start with 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3, right? So, if you look at this group here, and then you want to compare it with this group here, 0, 1, 2, 3. This is the group Z mod 4Z. That is, it's addition mod 4, right? So let's call this H, and let's call this G, right? I mean, these groups obviously are different, but there's something about them that's really the same. Because even if you multiply two elements, like 2 to the 1 times 2 to the 2, as we saw before, let's say 2 to the 2 times 2 to the 3. As we saw before, those are elements of G. This is the same as 2 to the 5, which is really the same as 2 to the 1, because we're taking 5 mod 4. Right? But that looks very similar to just working mod 4. It's like kind of like this whole group seems to be just kind of like working with the powers here. So, I mean, intuitively we get the sense that, I mean, group G and group H have the same size. That's one thing we know. They have the same size. This has 4 elements, that one has 4 elements. And the multiplication of elements here seems to be just concerned with adding powers. And the powers are being taken mod 4. So this group here and this group here they look different, but they seem to be very related. Is there a sense in which they are the same? Well, that question is answered by the idea of an isomorphism. That is, if you want to prove that, to kind of capture the idea that G and H are the same, all you'd have to do is to get a function from G to H, prove that phi is a function, of course, prove that phi is a homomorphism, and prove that the homomorphism is a bijection. That is, if you can produce an isomorphism between G and H, then you're showing that G is in a sense the same as H. This is the symbol for homomorphism, that isomorphism. A group G is said to be isomorphic to a group H, and we write it like this. If there exists a bijective homomorphism between G and H, or an isomorphism between G and H. Right, so those are the important ideas, and we'll need these when studying Cayley's theorem. All right, this has really gone on for a long time. Okay, so I don't know if I need to summarize anything here. Well, we've done quite a lot, so let me just summarize it so the ideas can stick better. Phi from G to H is a function. If G and H are groups, and we have the property that phi of G1 times phi of G2 equals to phi of G1 star phi of G2. If we have this property where dot is the group operation for G and star is the group operation for H, if we have this property right here, we say that phi is a homomorphism. But furthermore, if phi is also a bijection, That is, if phi is a bijective homomorphism, then phi is said to be an isomorphism. And in particular, what that means is that G and H are really the same group, look disguised. It looks different, kind of like here. This group and this group look different, but they're essentially the same. And so if phi is an isomorphism between G and H, we write that G is isomorphic to H. Isomorphic kind of means like equal. The two groups being equal. All right, so this is really what I have for you today, and this is going to be an important concept to us. We'll need it later when you're trying to understand or present a proof of Cayley's theorem. So in the next video, we'll talk about we'll give an intuition for Cayley's theorem, or maybe we'll do the intuition first. We'll see. All right. Anyways, thank you very much for listening, and bye.